Tangent planes and linear approximations. So earlier in calculus, we learned that as we zoom in towards a point on the graph of a differentiable function, the graph becomes indistinguishable from its tangent line, and we can approximate the function by a linear function. So here we're going to do it similarly in 3 dimensions. So as we zoom in towards a point on the surface um, of a graph of a differentiable function of 2 variables, the surface looks more and more like the tangent plane. So we can approximate the function by a linear function of 2 variables. We extend the idea to functions of 2 or more variables. You can see this in this graph here. The blue curvy graph is the surface, and in it we have curves 1 and 2, so C1 and C2. And we also have the brown, the tangent plane. So as we zoom in closer and closer, then we can see that the graph approaches the tangent plane, which is flat. And on it we have here we have pictured 2 intersecting tangent lines. So we're going to use this idea to develop the idea of the equation of a tangent plane. And the equation of a tangent plane is going to be very similar to what we've seen before. And let's say that z minus z sub 0 equals the partial derivative with respect to x, which is your slope for x. And we have x minus x sub 0 plus your partial derivative with respect to y, and y minus y sub 0. So your equation for your tangent plane is not hard. If there were more variables, let's say a, we would say the derivative with respect to a, that would be an a minus a sub 0. So however many dimensions you're in, your tangent plane can contain that many pieces. One thing to note, this is your partial with respect to x of x comma y. So you're not taking, these are times in here, it's f of x. It's the partial with respect to x times x minus x sub 0, and the partial with respect to y times that, and the partial with respect to a, because each of these is the function times the parentheses y minus y sub 0. So don't get that confused. Now, if you notice, this formula is also very similar to your point slope form from algebra. Y minus y sub 0 equals m times x minus x sub 0, where your m's are your partial derivatives in here. So it's very fun that it's the same thing stepped up. So let's do one here. And it says find the equation of the tangent plane to the elliptic paraboloid z equals 2x squared plus y squared at the point 1, 1, 3. I think it's always helpful to start with your formula. So z minus z sub 0 equals your partial derivative with respect to x times x minus x sub 0 plus your partial with respect to y times y minus y sub 0. Let's begin and let's start with the partial with respect to x. The partial with respect to x is, we have this elliptic paraboloid, and the derivative with respect to x is 4x. And then you're going to plug that in at the point 1, 1. So we get 4 for our partial derivative with respect to x. Now let's find our partial derivative with respect to y. And the derivative of that function would be 2y. And then when we use that at the point 1, 1, then we plug in 1 for y and we get 2. Now the reason we're doing that is we have a z is equal to the function xy. We have the point 113, but z is equal to the function xy. So that's why we're using the point 1, 1 in this conversation. So now we say z minus 3 equals our partial with respect to x, which is 4, times x minus and x sub 0, the x from the point is 1, plus the partial derivative with respect to y is 2, times y minus 1. Some instances, they want you to stop here. I never think that's a true statement. So z minus 3 equals 4x minus 4 plus 2y minus 2. So we solve this with respect to z, so we get 4x. We have plus 2y. We have minus 4 minus 2 makes minus 6, plus 3 is minus 3. So this is the equation of the tangent plane to that elliptical paraboloid. So you can see the picture here. We have the elliptic paraboloid and its tangent plane. And as we zoom in and get closer and closer to this point, then our elliptic paraboloid appears to be closer and closer coinciding with the tangent plane. Let's do an interesting example, and let's let z equal the natural log of x minus 2y at the point 3, 1, 0. Because, the examples in the text are never as good as the problems. The problems are interesting, not just a nice little elliptical paraboloid. So in order to find the equation of the tangent plane, we're going to start off with the partial derivative with respect to x. So the derivative of natural log of something is 1 over the something, times the derivative of the something is 1 with respect to x. So we have 1 over x minus 2y. So when we plug in our point of 3, 1, then we get 1 over 3 minus 2, which is 1. Nice. Now we're going to do our partial with respect to y. And when we do that, the derivative of the natural log of something is 1 over the something. And the derivative of the something with respect to y is negative 2. So we have negative 2 over x minus 2y. So now we're going to look at this with respect to the point of 3, 1. So we get negative 2 over x is 3 minus 2 times y is 2. So we get negative 2. So we have z minus the z value is 0 equals the partial with respect to x is 1 times x minus 3 plus the partial with respect to y is negative 2 times y minus 1. So we get z equals x minus 3 minus 2y plus 2. So z equals x minus 2y minus 1, the equation of the tangent plane. It says to graph the surface and the tangent plane at the given point. I am not going to require you to graph on a test. When you do this, I want you to do it in Desmos and actually look at it in 3D and zoom in and out and play with it. I'm not sure. WebAssign, I think, just pops the graph on there for you. It says choose the domain and the viewpoint so you get a good view of both the surface and the tangent plane. Then zoom in until the surface and the tangent plane become indistinguishable. So let's start with our formula. And our formula says z minus z sub 0 equals the partial derivative with respect to x times x minus x sub 0 plus the partial derivative with respect to y times y minus y sub 0. And we have the point 115 and z equals this beautiful equation right here, which is an elliptical paraboloid. So our partial derivative with respect to x is 2x plus y. And when we plug in these values of 1, 1, we get 2 plus 1. I don't know why I wrote that, but 2 plus 1 equals 3. And then our partial derivative with respect to y, we start with the first term, the derivative is 0. The second term, the derivative is x. And the next term, the derivative is 6y. So when we plug in our point of 1, 1, we get 1 plus 6, which is 7. So now we can do z minus the z value of 5. Our partial derivative with respect to x, our slope of 3 times x minus 1, plus our partial derivative with respect to y, 7 times y minus 1. So we get z minus 5 equals 3x minus 3 plus 7y minus 7. So z equals 3x plus 7y. And on this side, we have minus 10 plus 5 makes minus 5. So this is our equation of our tangent plane, and this is our function. So let's talk about the fact that when you go into Desmos, you can choose the 3D option, and I want you to do it. So go do that, come back. Hopefully you could see your elliptical paraboloid, your tangent plane, and let's head on to the next topic, which is linear approximations. So when we did linear approximations before, we just did the linearization is the point in, let me move this down. We did the linear approximation of x is equal to f of a plus f prime of a, your slope times x minus a. So as we move this into multifunctional, multivariable functions, you can see that it gets extended to, we're looking at partial derivatives, and then the linearization formula is very much similar, and we can use it to approximate the plane at a specific point AB. This leads us into our definition of differentiable. So if z equals f of xy, then f is differentiable at AB if delta z can be expressed in this form. Delta z equals the partial derivative of f at AB times the change in x plus the partial derivative with respect to y of AB times the change in y plus epsilon 1 delta x plus epsilon 2 delta y. where epsilon 1 and epsilon 2 approach 0 as delta x and delta y approach 0, 0. Now, that's a beautiful differential equation, but let's make it a little more practical. So this theorem is very useful. Remember, a definition is a given, and a theorem has been proven, and it's proven in the appendix of your book. So if the partial derivatives with respect to x and with respect to y exist near AB and are continuous at AB, then f is differentiable at AB. So catch the continuous part. So in order to show that a function is differentiable, you take the partial derivatives, and if they're continuous at AB, then f is differentiable at AB. That's super important. The problems are going to ask you to explain why the function is differentiable and then find the linearization. That's why we're doing this all at once here. Okay, it says explain why the function is differentiable at the given point, then find the linearization of the function at that point. We're going to start with the partial derivative with respect to x. So we're going to say the partial derivative with respect to x is 3x squared y squared. And then at that point, at negative 2, 2, when we plug this in, we have 3 times 4 times 4, which is 48. Now we're going to find the partial derivative with respect to y. So we get 2x to the third y. So when we plug in that point of negative 2, 2, we get 2 times negative 8 times 2, which is negative 32. Now, to explain that it's differentiable, we know that this function, let me put a box here. This function is continuous. It has no breaks. This function is continuous at the point negative 2, 2. Therefore, it is differentiable at negative 2, 2. So since they're both continuous, we're differentiable. That's good. So we're going to say, therefore, differentiable. Now, WebAssign is just going to ask you for the partial derivatives, and then I think you're going to have to say that it's continuous. Then we're going to look at linearization. Remember that our linearization formula says f of xy, they use AB, f of AB plus the partial derivative at x at AB times x minus a plus the partial derivative with respect to y at AB times y minus b. If we look at what we have this value, we have a, we have this value, we have b. We don't have this value, the function at ab. So let's go back up here and say f of negative 2, 2 equals negative 2 to the third is negative 8 times 2 squared is 4, which is negative 32. So now we can plug this into our linearization formula. So we're going to say the linearization at xy is equal to negative 32 plus our partial derivative with respect to x at AB is 48 times x minus negative 2 plus our partial derivative with respect to y at AB is negative 32 times y minus, and the b value is 2. So our linearization is negative 32 plus 48x plus 96 minus 32y plus 64. So our linearization at xy is equal to 48x minus 32y plus 128. So this is our linearization at xy, specifically at the point negative 2, 2. So the linearization of the function. Those aren't really difficult. They're not too bad to do. Remember that if it's differentiable, if it's continuous. Let's look at another one. The directions are the same, where it's supposed to explain why it's differentiable and then find linearization at the point 2, 4. And f of xy is equal to 7 plus x natural log of xy minus 7. So let's go ahead and find the partial derivative with respect to x. So the 7 is a constant. We're going to need product rule here because we have two functions happening. So I'm going to take the derivative of x to be 1, and we have natural log of xy minus 7. Plus, we're going to keep the x, and the derivative of natural log of something is 1 over the something, and the derivative of that something is y. So our partial with respect to x is natural log of y minus 7 plus xy over xy minus 7. Now, is this continuous at the point 2, 4? You have to think about the domain of these functions. The domain of this natural log function right here says xy minus 7 has to be greater than 0. So xy is greater than 7. We're going to put a 7 here, not a 0. And then the domain of this function is xy minus 7 cannot equal 0. So xy cannot equal 7, which gets absorbed here. So this is differentiable when xy is greater than 7. So 2 times 4 is 8, which is greater than 7. Therefore, we are differentiable at 2, 4. So let's go ahead and plug in 2, 4. So we're going to say this value at 2, 4 is natural log of 8 minus 7 is 1, plus 2 times 4 is 8 over 8 minus 7. So natural log of 1 is 0, so we have 8 over 1, which is 8. Nice, pretty number. Love it. Now let's talk about our partial derivative with respect to y. The derivative of 7 is 0 because it's a constant. When you look at this, this is not product rule anymore. The x out front is a constant, so we're going to keep the x out front. And the derivative of natural log of something is 1 over the something, times the derivative of something with respect to y is x. So this gives us x squared over xy minus 7. So that's a nice, pretty function. Now let's talk again about the differentiable. So the domain of this is xy has to be minus 7 does not equal 0. So xy cannot equal 7, which happens for us here because it's differentiable when xy does not equal 7. And 2 times 4 is 8, so we are good. So let's go ahead and plug our point in, and we're going to say the derivative with respect to y at 2, 4 is equal to 2 squared, which is 4, over 8 minus 7 is 1, so now we have 4. Now we have to go back to the original problem because we know that for our linearization, we need the f of ab. So let's say f of 2, 4. Well, let's go back up to figure it. So when we come up here, we're going to say f of 2, 4 is equal to 7 plus 2 natural log of 8 minus 1. 8 minus 7 is 1, and this makes 0, so we have 7. So f of 2, 4 is 7. So now we can find our linearization. We're going to say the linearization of xy, this function, is equal to f of ab, which is 7, plus the partial derivative with respect to x is 8, times x minus the x value of 2, plus the partial derivative with respect to y is 4, times y minus the y value of 4. So the linearization at xy is 7 plus 8x minus 16 plus 4y minus 16. So the linearization of xy at this point is 8x plus 4y, and we have negative 32 plus 7 makes negative 25. So minus 25, and that's our linearization of f of xy at the point 2, 4. Given that f is a differentiable function with the value being at 4, our xy is 6, 3, and the value is at 4. The partial with respect to x is at 1. The partial value with respect to y is at negative 1. Use the linear approximation to estimate 6229. The question is, why do we do this? Even before my day, before calculators, you could use linear approximations to come up with values that were difficult to find. Consider the fourth root of a value. The fourth root of 16 is 2 because it's easy. Fourth root of 81 is 3. But let's say you want to find the fourth root of 56. Well, you would need a linear approximation to do that. There's no good, easy way to extrapolate that. You would let y equal the fourth root of x, and then you could do a linear approximation to approximate that value. But we're going to do this problem here. I just needed you to have some idea. I don't believe linear approximations are used as much today as they were back then. So let's start with our linearization formula. We're going to do f of ab plus the partial with respect to x at ab times x minus a plus the partial with respect to y at AB times y minus b. So the linearization at xy is equal to the value at AB plus the partial with respect to x at AB is 1 times x minus a, which is 6, plus the partial with respect to y at AB is negative 1 times y minus 3. So you could probably skip this step. I'm going to go ahead and distribute because I have minus y plus 3. And then the linearization, I don't lose negatives if I'm careful. So x minus y, and 4 minus 6 is negative 2, plus 3 is plus 1. So our linearization of the function at that point is this value. Now, because we're using it at that point, we need to use it to approximate close to that point. So we're asked to approximate at 6.2, 2.9, which is very close. We're going to use this notation f. So we can approximate f of x at that point because it's very close to the given point 6.3. And in that case, it can give us an approximation. So we're going to say 6.2 minus 2.9 plus 1, and this gives us 4.3. The linear approximation is a helpful skill. It helps us to evaluate things that are hard to evaluate at points. We can also do linear approximations in 3 or more variables. You just have to add all of them in. For example, well, not for example, the notation would be L of xyz is equal to f of abc plus your partial with respect to x of abc times x minus x sub 0 plus your partial with respect to y of abc times y minus y sub 0 plus your partial with respect to z of abc times z minus z sub 0. So you can see how we can do our linear approximation even when we have extra variables involved. So when we talk about differentials, it's very much what we did in chapter 3 for Calc 1. And we can say that the differential is dy is equal to f prime of x dx. Remember that find a differential, we took the derivative, the implicit differentiation, and put the dx, dy, dz in there. So the relationship between the increment delta x and dy, you can see that happening in this picture. So delta y represents the change in the height of the curve, and dy represents the change in the height of the tangent line. So it's talking about the curve versus the tangent line. And so we have a differential formula down here where we take the partial derivative with respect to x and put dx, partial derivative with respect to y and put dy. So it can be used as this notation as well. You can see that this ties nicely into the 3D space. We're looking at the tangent plane versus the surface. So let's look at finding a differential. So this problem says let z equal f of xy equal x squared plus 3xy minus y squared. Find the differential dz. So let's go ahead and jump in. Let's say dz equals the derivative of x squared is 2x dx, the differential, plus, now we're going to have to use product rule here. So I'm going to keep the 3 with the x. The derivative of 3x is 3, and we keep the y with respect to x, plus the derivative of, we keep the 3x, and the derivative of y is 1 dy, minus the derivative of y squared is 2y dy. We're going to clean this up a little bit and say dz equals, we have two dx terms, so let's say 2x plus 3y dx plus 3x minus 2y dy. So you kind of group them so that you have one dx and one dy. Let's look at one more. It says let z equal e to the minus 2x cosine 2 pi t. So we're going to start with dz equals, then we have product rule, we have e to the minus 2x, and we have cosine of 2 pi t. So let's start with the first one. The derivative of e to the minus 2x is e to the minus 2x, and the derivative of the inside is minus 2. and we keep the cosine of 2 pi t, and this derivative was with respect to x. Plus, we keep e to the minus 2x, and the derivative of cosine of something is negative sine of that, and the derivative of that is 2 pi, and then we have dt. So dz equals negative 2 e to the minus 2x cosine of 2 pi t dx minus 2 pi e to the minus 2x sine 2 pi t dt. All right, let's look at one more. This is our great application problem. It says use differentials to estimate the amount of metal in centimeters cubed in a closed cylindrical can that is 18 centimeters high and 8 centimeters in diameter if the metal in the top and the bottom is 0.4 centimeters thick and the metal in the sides is 0.05 centimeters thick. Round your answers to decimal places. So the volume of a closed cylindrical can is volume equals pi r squared h. Pi r squared is the volume of the base, and you multiply it times the height of h. So we're going to find the differential. So we're going to say dv is equal to pi. We're going to take the derivative of r squared to be 2r. So let's say 2 pi r h dr. Plus, we're going to keep the r squared in the derivative of h. So we're going to say pi r squared dh. Now we're given values, so let's go plug in what we have. So dv is what we're supposed to estimate the amount of metal in the can, the volume. So we're going to say 2 pi, and the radius of this figure is, it's 8 centimeters in diameter, so the radius is 4 centimeters, and the height is 18 centimeters. And the thickness of the radius, the dr, is 0.05. And then we have pi times the radius, which is 4 squared, times dh. Now, the thickness of the top and the bottom is 0.4, but there's two of them, so you're going to double it to be 0.8. So we get 62.83 centimeters cubed. I hope you enjoy this lesson and have learned a lot.